Today I'm going to discuss backpropagation in artificial neural network. Backpropagation is an algorithm implementing that allows machine learning for neural networks. Mm, By applying backpropagation, we are able to solve multiple classification problems and also regression problems with the use of neural networks consisting of several hidden layers. Okay, so now I will try to uh, show some example of neural network, which will be the good point to start discussion. Um, okay, so let's consider this one. So there are no biased neurons, however, they should be because usually they are in each neural network. But the general idea is to make it simple so it's easy to understand for everyone. So as you can see, this neural network consists from one input layer, uh, one hidden layer, and one output layer. Um, each neurons are connected with edges, and each of the edge has its own weight. So how the neural network works when it predicts values is just uh, calculating the inputs of several neurons uh, based on the weight. So the weight decides how strong is the connection between neurons. Yeah. So as a result of backpropagation algorithm, as a result of this machine learning, some connections become stronger and some connections become weaker. Yeah, and the combination of those connections allows us to fit the network to some specific problems, like to realize some closed game decisions, or to play some games to recognize pictures and so on. Okay, so the uh, prediction starts from applying some input vector with values to the input layer. Then we are feeding forward all the neurons. For example, we let's consider this H2 neuron from hidden layer. So its value after applying the values to input is A1 times W2 and A2 times weight 4, which is the net of value of the neuron. Uh, it's not sufficient to allow the neural network to learn. We need to activate this value, this net of value, by introducing some non-linearity to it. Um, in this example, I will use the sigmoid function, but it can be also ReLU function, hyperbolic tangent function. It can be softmax function. So there are plenty of activation functions we can use in neural networks, and the results depends on what type of activation function we are using for specific neurons. So in this case, it is it is sigmoid. So it's 1 divided by 1 plus e power to minus net value of specific neuron. Um, Here is the chart showing how the sigmoid function looks like. So as you can see, there is some space between -4 to 4 where we have non-linearity, and this is the area when we are trying to be during the learning process. Yeah. Um, okay. So and this is also applied to the output neurons. So the net of value is calculated in the same way. So we are just taking the input edges and multiplying weights by input values of connected neurons. In this case, H1 and H2 multiplied by W6 and W8 respectively. Okay, so at the end, we end up with some output values calculated by this neural network, and we are now able to start calculating the error. I mean, the distance, how far are we from the expected results? Backpropagation algorithm is highly connected with stochastic gradient descent. Actually, by by implementing by performing backpropagation, we are realizing stochastic gradient descent idea, which simply assumes the changing the weights, so the gradient of the cost function becomes zero. This is the goal. So in this particular example, as we calculated two values, which are, for example, 0.0056 and 0.7432, which are a bit not exactly which are not exactly our target, which is 0 and 1. So you can quickly guess that this neural network, as the goal of this network is to do simple negation of input values in this particular case. Now we are able to calculate error. We have several error equations to use. One of the most popular is mean squared error, but also we can use cross entropy along with softmax activation. So this is just one of the example. So mean squared errors just represent a sum of subtraction between target and predicted value power to 2 divided by the number of neurons in output layer, the size of the output vector. Now let's imagine the cost function. Actually, the error function is a cost function, but if we consider specific individual weight, we can imagine that this cost function could looks like this, and our initial weight is at some point on this line, and the goal is to change the weight with each iteration of the learning process of the backpropagation, so it reaches the minimum value. It doesn't need to be zero, but it has to be minimum value. Yeah. So we are achieving this by calculating partial derivatives of some error, of total error with respect to specific wave associated with the edge. On the left, you can see the basic formula for in case wave W8. We are decreasing it by subtracting the derivative of total error with respect to change of this wave multiplied by eta, which represents some fixed learning rate. A learning rate can be found arbitrary. It's just a constant. Okay, again, if we take the general idea of backpropagation, it's about first feeding forward the neural network. So we are realizing the prediction process, activating neurons in each layer, and calculating output values. And having those output values, we are calculating the error. Now, backpropagation starts from the very last layer. This is the output layer, and for this layer, we are getting all the input edges for each neuron, and we are calculating derivatives of error with respect to each wave, so we can subtract this from each wave. And we are repeating this procedure for each neuron in the layer. If we finish with the layer, we are switching to the next layer. This is hidden layer. We are doing exactly the same. We are subtracting partial derivatives. Once we get to the input layer, the iteration is finished and our weights are updated. Okay, now let's look closer at some mathematical formulas by using specific weights from this graph. So we will have a better feeling how this works. So let's say we would like to change the weight of weight 5 as a result of backpropagation. We calculated the total error, and we need to calculate the derivative of this total error with respect to this particular weight. We cannot do it directly because it's not possible. We need to apply so-called chaining rule. It was invented by Leibniz, a very famous mathematician. So the goal is to optimize this weight, and that's why we are using derivatives to make it accurately. Okay, so as we are using the chain rule, we can see that we can dispatch this this equation to three components, which are nicely reducing with each other. As you can see, the first component is derivative of the total error with respect to output value of specific neuron. The second component is derivative of output value with respect to netto value of this neuron. And the last one is the derivative of netto value of this neuron with respect to this concrete weight that we are going to change. Okay, now we are trying to break down the first component of this equation. So we know that our total error is the mean square error, and this is polynomial. In this equation, the y is actually the same like O, so we can treat it as an output value of the neuron, and t is our target value from our expected values vector. So by following simple mathematician rules, we end up with t1 minus O1, so which is very simple value to calculate. The next component, it's just a derivative of the sigmoid function, and we know that the derivative of the sigmoid function in terms of the output value of the vector is output value times 1 minus output value of this vector. So it's also easy to implement. And the last but also important fraction of this equation, so derivative of net value with respect to change of the weight. So as the net value is a sum of the multiplication of input values from the previous layer and specific weights. If we are doing the derivative with respect to W5, we end up just with H1 value, which is also very simple. So for this output layer, we are doing that kind of calculation for each of the edges that are hitting our neuron. Of course, by this occasion, when it comes to the implementation, we can save some information that we have calculated in advance, because they might be helpful if we switch to the preceding layer, in this case hidden layer. Okay, now let's consider calculation for the hidden layer. Let's say we are going to optimize weight 1. So this is our well-known equation where we have the learning rate incorporated and the derivative of total error with respect to this weight. As previously, we cannot calculate this derivative directly. We need to apply the chaining rule as well. But now it looks a bit different. But we also follow the same idea. So the derivative of total error with respect to H1 value times derivative of the H1 value with respect to its netto value times net value of H1 with respect to change of W1. So as you can see, it nicely reduces to the E total slash delta W1. Okay, now let's break down the first component. The first component is the sum of errors with respect to the change of the output value of H1. E1 and E2 are the errors for the coming from neurons from the following layer, in this case output layer. Now let's try to break down the first component of this equation, and analogically it will be the same for the second component as well, which I'm not going to show you right now. Okay, so change of error 1 with respect to change of H1 value. Following the chaining rule from Leibniz, we are using delta E1 with respect to delta netto value of O1 times netto value of O1 with respect to delta H1. So it's nicely reduces, but we still don't know how to calculate those two components. So now let's break down the first one. So we are using, again, chaining rule, and we know that total error with respect to change of output value that we calculated in a previous layer times change of output value of previous of neuron from previous layer with respect to change of netto value of this layer will give us the first component. Yeah, so you can see it's reducing very smoothly, and the right hand component is a simple derivative of netto value of the output neuron with respect to H1. So as you can see, it's just simply W5 because we are derivating by H1. The same equation, the same set of equations, of course, but with different indexes, we can apply to the right-hand component. Yeah, and the middle component we are calculating in a different way because it's again the derivative of sigmoid function, which we discussed earlier. So in this case, it will be H1 times 1 minus H1. And the very last component is the net value of H1 with respect to W1, which is simply A1. And we are repeating this procedure for each neuron, and we end up with the optimized weight at some points. Of course, there's a danger that we hit some local minimum. So we need to take care about. There are different methods to protect from this behavior. We can use smaller weight, smaller learning rate. If we use too big learning rate, we might end up with not fitted neural network. So we can also use the SGS algorithm to get some progressing learning rate, yeah, depending on how fast our neural network is learning. So this is basically it. So my experience with this calculation is quite positive. I was able to implement a simple framework allowing back-propagation and learning of simple neural networks consisting of dense layers in Java. I will publish this soon. But in general, in practice, you will use some libraries out of the box like Keras, Tensorflow, allowing you to design neural networks and do some predictions with the use of them. But it's good to know how the formulas are shaping behind this learning process of neural networks. This is kind of kind of first steps in order to understand machine learning. But it's quite a big step in my opinion, because you know, multiple things might change, like activation of functions, learning rates, approach to distribute weights. Um, so there are several knobs that you can tweak, right? But the concept is generally the same. Um, okay, so thank you for now.